Thank you all for joining us today. We'll be getting started in about 2 minutes.
Hi, Juan.
Hi. Hi, Tony.
Nice to see you. I don't know why I had the technical problem, but Veronica, you and I maybe, I noticed that none of the seminars now have the panelist link. Something weird happened, but anyway. And Juan, I'll see you again on Friday.
Yeah.
Very good. Thank you for joining us today.
Thank you for inviting me.
Did you get my email the other evening about?
Yeah, I got it. Sorry, I just got a bit busy with the SML, so I haven't got a chance to reply to you yet. Yeah, but I got the you talk title and abstract. Thank you.
Okay.
Yeah.
Yeah, if you could just give me the answers to my questions, I'll adjust accordingly. Thank you.
Yeah, I'll do it like right after my talk. Yeah, sorry.
Yeah, no worries.
Yeah.
All right, it is 11:04. I think we can go ahead and get started. Yinzi, I'll pass it over to you.
Sure. So good morning, everyone. So thanks for joining this exciting seminar. So great to have Huan, who is actually at Baltimore right now doing a virtual talk in your hotel room. Huan is a postdoctoral researcher at CMU. So he received his PhD degree from UCLA in 2020. And his research focuses on the trustworthiness of artificial intelligence, especially on developing further verification methods to guarantee the robustness and safety of machine learning. He was awarded with an IBM PhD fellowship and also lead the winning team in 2021 International Verification of Neural Network Competitions. He also received 2021 ML Rising Star Award sponsored by MIT and IBM Watson AI Lab. That said, without further ado, we'll have Huan to present his talk.
Yeah, thank you to introduce for the introduction. And can you see my screen? I start sharing.
Yes, we can see that.
Okay, cool. Yeah, thank you for the introduction. And yeah, I'm actually at Baltimore for SML for the exciting conference this weekend. But I have this got this invitation for this talk a few months ago, and it was scheduled for a virtual talk. So that's why I'm just actually doing a virtual talk, even if I'm physically presenting physically at Baltimore. Okay, cool. Thanks for the introduction again. I'm very honored to give my talk at Johns Hopkins. And in this talk, I'm going to present my work on neural network verification, where we want to formally prove the trustworthiness of a neural network. So when applying neural networks to many real-world tasks, we often want to ask if the neural networks are reliable enough to be used for some mission-critical tasks. For example, it's not uncommon an autonomous driving system utilizing neural networks-based computer vision techniques to detect, for example, road signs, pedestrians, or other important objects around the car. And the failure of detection can lead to a death. And similarly, in medical system, a malfunction of equipment or wrong diagnosis may also kill people. And in security system, we also ask the neural network to detect suspicious objects or people and evasion of surveillance may cause loss for the object under protection. So the big question here is, can we trust the outcome of a neural network and make sure it behaves predictably and reliably when it is applied to these mission critical settings? So unfortunately, the answer is most likely no, because researchers have found that neural networks actually can be unreliable and behave quite surprisingly under many realistic scenarios. For example, there's a paper at ICCV 2021 where researchers showed that by changing the illumination of the stop sign using a cheap projector, they can actually trick the road sign detector, and stop sign will be recognized as a speed limit sign. This can lead to critical consequence for self-driving. And in medical applications, people also find that a simple rotation of the medical image will flip the outcome of a neural network. And if you just change a few words in medical records, and the outcome of the neural network can also be easily changed. Surprisingly, this may lead to misdiagnosis. And these things are usually called out-of-cell examples, and we know them for a few years, and people know out-of-cell example exist for many applications, not just what I showed here. And to really confidently use neural networks in these critical applications, we have to somehow formally verify the behavior of a black box neural network. At high level, what neural network is doing is sort of like program verification, where the traditional program verification, you have an input for your code, and you have some code, and you have some desired specifications for the outcome of your program. For example, it needs to behave correctly under any reasonable under any legal inputs, and it should not deadlock, it should not have bugs, for example. And for neural network, it's doing we are trying to do the same as a neural network. We're just replacing the code as a black box with a black box neural network function. Because neural networks actually are replacing some of those fixed function code actually in some as a building block in some more complicated systems. And we want to see like how the neural network behave, and we also want to formally verify the behavior of a neural network, just like what we did for program verification. And let's take a simple example, which is robustness verification, where we want to verify the robustness of the neural network, which is one of the most simple application for verification. For example, in the robustness verification setting, we have the specification that basically saying that for some input X, that is around the original input X0. That means, for example, you can add in some noise to the image, and we want to show that actually the prediction of the network should always be the same. For example, I have a dog image, and I add some noise to the dog image, and I can tell you that like the noise added is just a small amount, and it won't actually change how the picture actually looks like. But what we really want to prove is like that we want to show that the network is always predicting the image as a dog, never as a cat or any other classes. And on the left, bottom left corner, it shows a case where the neural network is not robust because there is a point, the red point down the figure, that's across the decision boundary and also within the perturbation set that actually makes the network thinks the dog image is actually a cat image. On the right hand side, where we could prove that actually the network is robust because it will never cross the decision boundary. For verification, what we really want to do is to find a formal proof to verify that the network will never change its prediction under any bounded noise, under any bounded perturbation that is within the perturbation set. Is basically this blue ball here. And in the robustness verification setting, you cannot just do adversarial attacks and show, hey, I cannot attack this classifier, so it's gonna be provably robust. And that's not true, because it's most likely your attack is not stronger enough, and if someone else find a even stronger attack, they can break your system. So, but however, if your model is formally verified, then I can tell you for any attacks that is under our consideration, which is within this perturbation set, I can actually tell you that there's no adversarial examples. You can never successfully attack this network. But this is just one application of neural network verification. We can actually use neural network verification to do a lot of things to verify not just robustness. We can also verify safety, fairness, spontaneity, correctness. Basically, you need to formulate your requirement as some sort of mathematical formulation, and eventually we'll be able to verify if that specification holds or does not hold using a neural network verification tool. And in the very simple setting, let me just introduce the most easy setting here. It's for robustness verification with a binary classifier. And with a binary classifier, suppose the input is x0 and the output is fx0. And suppose here the output is just a score. When it's positive, we see the x0 is a positive example. When it's negative, it's a negative example. And in that setting, suppose the original input x0 is a positive example. And what we really want to show that is for a neighborhood around x0, the classifier always predicting a positive number. And if we can show that true, then we know it's going to be robust. For example, in this figure, if we can show for every point within this green box, the network is always predicting cat, not a dog, then you know it's robust against all perturbations within this green box. And of course, one way to checking this, you can enumerate all the points within the green box, but that's most likely impossible because the input space is continuous and there are infinite number of points. And so that's why actually you need specialized algorithm for the verification problem. For example, by considering this binary classification problem, a neural network verifier sees the input as a perturbation set rather than a single point. And in that setting, the output of the neural network is also a range of scores rather than just a single value. Suppose I can, for example, using some way to enumerate every possible point within the perturbation set, then I can determine the range of the output for the neural network. For example, if the output range is between 0.2 and 2.2, then I know you can never flip this positive example to a negative example. Then you can show that actually the network is robust and is provably robust. So the basic formulation for robustness verification is that assuming you have a positive example, you're trying to minimize the function within the perturbation set such that you find the minimum value. If that minimum value is greater than 0, you know it is provably robust. If the minimum value is less than 0, actually you find some x star that can flip the output and makes the network predicting a negative label. So then you have a adversarial example, the network is not robust. So this problem mathematically looks very simple, but actually it's not that simple to solve. The main reason is because the formulation has a neural network involved, the fx, the neural network function, and it's highly nonlinear and a non-convex function. And if you just do this minimization, for example, using gradient descent or whatever, gradient-based method, you won't be able to converge to the true minimum. If you're not getting the true minimum, you can never tell if there is a adversarial example or not, and there's no way for you to prove to formally prove the network is robust or not. One way of thinking this optimization problem is by seeing this as a constraint optimization problem. So for example, we have the output of the network defined by ZL, which is basically the feature of the output layer of the neural network. And we write out all the equations that defines the neural network, which involves these linear constraints and the nonlinear constraints, and also the input perturbation constraints. what is really tricky here is nonlinear and nonlinear and non-convex constraint on these activation functions, such as popular ReLU functions used in neural networks. That makes the entire problem non-convex, and it's really hard to find a solution for this problem. So let's look at this constraint more carefully. So this says basically that the output of the ReLU layer equals to the input of the ReLU layer. Apply a ReLU function. That basically says the feasible solution needs to be on the graph of the ReLU function, and the graph on the ReLU function is actually a non-convex set consisting of two lines. And one formulation to solve this problem is to use mixed integer programming. I can use existing mixed integer programming solver to solve the problem, but it's going to be really, really slow. One of the early approach to do verification is just to formulate the neural network work as this formulation, and then you can solve the verification problem using a MIP solver. But that's going to be really slow because MIP solver are not designed for problems that are as big as a neural network. You can have thousands or even millions of neurons, and you can even for smaller networks, it can take hours or longer to run a MIP solver. And another more practical way of doing verification is the so-called incomplete verification. Is that instead of finding a lower bound of the original objective, or instead of finding the true value of the original objective, you find the lower bound of the original objective. So if the lower bound of f star is greater than 0, you know the true value of f star is greater than 0. So you are going to prove the network is robust. Otherwise, if the lower bound is less than 0, then you can't tell if the network is robust or not. The verifier basically say, I don't know. That's why it's called incomplete verification, because there are cases it cannot tell if the network is robust or not. So in this talk, I will introduce basically the bound propagation-based framework I developed during the last few years to formally verify the robustness and other properties of neural networks. And all the algorithm I will introduce later will be able to run on GPUs and do not rely on CPUs or MIP solver or LP solver. And we actually can use GPUs, and we can do optimization on GPUs to tighten those bounds. And we can also combine our method with branch and bound, which greatly improve its power and tightness. So overall, I will briefly introduce a series of algorithms, cron, auto-layer-path, alpha cron, and beta cron. That actually built after alpha beta cron toolbox. That is one of the state-of-art neural network verification toolbox for, and we actually win the competition last year for neural network verification. And so let's just briefly go over this bound propagation based verification algorithms and see how they work. And we know we want to find a lower bound of the minimization problem. And the cron is an algorithm that can actually give you a linear lower bound for a highly nonlinear and convex neural network function. For example, on this figure, the neural network function is fx, and it is a non-convex function, and it's really hard to find a minimum within the perturbation set. But what cron does is it finds a linear lower bound of the original function, and it guarantees to be a lower bound for any x within the perturbation set C. And we can easily calculate the lower bound of a linear function, and that of the linear function is called f star cron, which can be used as a lower bound of f star for incomplete verification. So assuming we have a linear neural network without those ReLU neurons, because as I just mentioned before, the issue happens when you have ReLU neurons, which is nonlinear and non-convex. And after you're removing all the ReLU layers, and you can actually multiply all the weights of the network together, and the network becomes just a simple linear function. And in that setting, actually, it's going to be much easier to do the verification, because for linear network, you can actually apply Holder's inequality to get the exact lower bound, exact bound of this objective very easily. But the issue is we do have ReLU function, and how to handle these ReLU functions in neural networks. And the trick we used is by approximating these ReLU functions using their linear lower and upper bounds. For example, we have the ReLU function, which I have on this plot here. And I know the ReLU function is with the input of the ReLU function is within the range L and U, and that's called the pre-activation bounds or intermediate neuron bounds or whatever. And if you know the input of the ReLU is within that range, and then you can lower and upper bound the ReLU function using the two blue dotted lines shown here. And after you're replacing this nonlinear ReLU function with the two linear bounds, you can actually somehow linearize the network and also obtaining a sound lower bound of the network. I will quickly show you how that is done. So the bound propagation algorithm works by propagating a lower bound for the output neuron with respect to the hidden or input neuron. It's basically propagating from the last layer through all the intermediate layers until you reach the input layer, so you can get a linear bound of the output with respect to the input node. For example, I have a simple neural network here with 3 weight layers and 2 ReLU layers. And the goal is to get a lower bound for fx within the perturbation set x belongs to C. And at the output layer, we know by definition fx equals to Z3, which is the output of the 3rd layer. That's by definition. By propagating that bound to the previous layer, because there's an equation by Z hat 2, which is Z hat 2 is the output of the 2nd ReLU layer. So all of this is done by definition. After that, you encounter this ReLU layer. And to handle this ReLU layer, basically you linearize the ReLU neuron using the linear lower bound and upper bound as we just introduced. And basically you replace the ReLU function with a diagonal matrix D that representing this relaxation. And also after you do the relaxation, you choose either the lower bound or the upper bound to make sure this inequality here still holds. So you get a lower bound for fx with respect to a hidden neuron Z2 in the neural network. And you just keep propagating this, and you encounter a linear matrix W2, and by just plugging the definition, Z2 equals to W2 Z hat 1, and you propagate into the next layer, and you encounter another ReLU function, and you apply this linear relaxation again by replacing ReLU with the diagonal matrix such that this lower bound still holds. And after doing all of those, you finally reach the input layer. After we reach the input layer, as you can see here, we actually get a linear function of the fx with respect to the neural network input x. This is what we had. We had called Huan linear lower bound. And here is the coefficients of the linear bounds, A and C, actually just a function of neural network width. For example, A here is just the WD, W3, D2, W2, D1, W1. If you can just multiplying all these numbers together, you get the coefficients for the linear bounds. And after getting a linear bound, what we really have is you got a linear bound for the non-convex function, neural network function fx within this perturbation set C. And after we get in lower bound, you can use that lower bound for verification. And the good thing here is the entire bound propagation process can actually be done on GPU, because as you can see here, it's just a bunch of matrix multiplications. You just need to multiply all the weight layers, and the D matrix is representing the linear relaxation of the ReLU layers together. And by multiplying that all together, it's just a bunch of matrix operations, and you can do that very efficiently on GPUs, just like what we do for neural network training. And after that, you get a linear lower bound for the neural network, and this is guaranteed lower bound for all input within this perturbation set. So this is a bound propagation algorithm, and this is a basic version. And we do have another version which takes the relaxation of the ReLU function into account. Because when we relax the ReLU function, we actually have different choices for the lower bound. For example, as you can see in this figure, we have 3 dotted lines here, which are all valid lower bound for a single ReLU function. And you can choose any of them. Actually, you can choose any line that has slope between 0 and 1. That means you have flexibility to choose. For any lower bound you choose, you can obtain a valid linear lower bound for the output of the network. And we can actually optimize this slope for ReLU relaxation to get the tightest possible bound. What overall we are doing is like, after you get a Huan linear lower bound, we can somehow tweaking this lower bound to make it even tighter and even closer to the fx function, such as you get even tighter bound. So here I just show a cartoon here. You have, for example, you have some parameters in this bound that's called alpha. You can actually optimize this alpha using gradient ascent on GPUs, and you can quickly make the bounds tighter by optimizing these parameters within bound propagation. So I won't be able to cover all the details of those algorithms. If you are interested in the details of all the details for the bound propagation algorithm, you can check out the tutorial at neuralnetworkverification.com, and we have videos plus slides, and you can get a more deeper understanding of how bound propagation works. And let's get into the easier part, which